This is a pleasure to listen to you again, and we hope to see you in the future in other projects.
Thank you very
Thank
much,
you.
and thanks again for the invitation and for your attention.
You're welcome. Then, Matthias,
Hi,
are you here?
everyone. Thanks a lot, Morelli, again. And we're now moving on the last part of the today's session. And remember that after lunch break, we will have perspective talk with Patricia Orcajada. So stay tuned after lunch and come back, please. Now we will have 3 speakers in our flash sessions, and the first one, in order to introduce her, I will do it in Spanish also, because she's from Argentina, although she's working now abroad in Professor Falcaro Group. So, Mercedes Linares Moreau, bienvenida, gracias por aceptar la invitación nuestra. Y bueno, esperamos escuchar tu presentación. Mercedes, she's graduated in physics at the Buenos Aires University and received a PhD from the University of San Martin, from UNSAM, in March 2018. And since then, she's working in Professor Falcaro Group as a postdoc in interest, among her interests, there is this heteroepitaxial growth of oriented MOF films and patterns with applications in optical sensing and microelectronic devices. Así que, Mercedes, es tuya la pantalla y bueno, estamos contentos de tenerte y bueno, adelante.
Muchas gracias. Gracias, Matías. ¿Se escucha bien? Oh. Can you hear me?
Yes, it is
Sí, se escucha
perfect.
bien.
So go ahead.
Okay. Okay.
So try to share your screen. It should be working.
So share. Okay.
Yeah, now we're watching your screen. Now it's the presentation. Perfect.
Oh,
great.
Okay.
Go ahead.
Perfect. Thank you. Okay, thanks a lot. I will start with some words in Spanish because I'm just happy to be able to share this with the MOF community in Argentina. So, muchas gracias por haberme invitado a formar parte de esta sesión y de este simposio. Y me parece una iniciativa muy buena, ya que hay tantos grupos trabajando en MOF en Argentina, que podamos colaborar también con las personas que estamos afuera. Así que bueno, muchas gracias por esta oportunidad. So it was just a few thank you words. So I'm going to talk today about the semi-automatic deposition of oriented copper hydroxide nanobelts for the heteroepitaxial growth of MOF films. So this is somehow a little bit in the topic of Min Tu's talk in the morning. He gave a very nice introduction about MOF films, so I will pick up on that point, let's say. But I want to start, well, most of the talk that I will give today is related to our recently published papers, so if in advanced material interfaces. So if you're interested by anything that I will discuss today, you can look for the paper to have more information about this. I wanted to start by highlighting the team that formed part of this work. So, of course, it was not only me, but we did this work with Lea, Thomas, Sumea, Francesco, and of course, Paolo Falcaro. We are working at the Paolo Falcaro Group in the Institute of Physical and Theoretical Chemistry in Graz University of Technology. We collaborated also with another institute, the Institute of Solid State Physics, with Professor Egbert Sawyer for some modeling and calculations, and we collaborated with Kenji Okada and Professor Masashi Takahashi from the Osaka Prefecture University in Japan, and also the work was co-led by Professor Christian Dunan in the University of Adelaide in Australia, who is a long-time collaborator of Paolo. So we all know what MOFs are, that's why we are here, I guess. But I wanted to start by highlighting how all the properties that we like from MOFs, the very high surface area, the possibility of tuning the physical-chemical properties, can be harnessed for applications of MOFs in functional devices if we can tackle all the challenges related to thin film processing of MOFs. So this was already introduced by Min in his talk in the morning. So in the Argentinian morning, in the early afternoon from Europe. He actually talked about heteroepitaxial growth of MOFs. So I will discuss about another approach for heteroepitaxial MOFs. In 2017, Paulo and coworkers published a paper in Nature Materials where they showed that it is possible to obtain macroscopically oriented MOF films by ceramic to MOF conversion from substrates, from copper hydroxide substrates that were originally also aligned. So from these substrates that are composed of aligned copper hydroxide nanobelts, which are these like anisotropic nanostructures that are around 200 nanometer long, after exposure of the ceramic to a solution containing the ligand, in this case terephthalic acid, this can be converted using the substrate, the copper hydroxide as a sacrificial template, to an oriented film, polycrystalline film, where the crystallites grow heteroepitaxially on the copper hydroxide. So by ensuring the lattice matching between by selecting a ligand and a MOF that has a crystal structure that is compatible with the crystal structure of the copper hydroxide, it is possible to grow these or MOFs that have that are macroscopically oriented. And this is interesting because, well, this has been extended for other linkers and other MOFs in this case are copper-based, of course, because we are using the copper hydroxide as a source for the metal cations. But it's interesting because in this way you can have oriented pore channels, which could be interesting for several applications. So for example, in this work by Okada in the Chemical Science in 2020, he studied and showed for different MOFs with different linkers the growth mechanism. So this concept was also extended to show that it's possible to have an approach of MOF on MOF and to grow inspired by layer developments like the ones from Professor Boll. But it was also possible to grow heteroepitaxially different MOFs with different ligands, one on top of the other, if the crystal structures were matching. So what I wanted to motivate is that it's not only one MOF, but that it's a platform, a system that is based on this ceramic to MOF conversion and subsequent MOF on MOF growth, which offers different possibilities for application to devices that rely on MOF thin films. So everything starts with the copper hydroxide nanobelts. We synthesize this according to a protocol that is in this paper, and this takes advantage of the fact that one of the crystallographic directions of the copper hydroxide grows much faster than the others. So just by controlling the reaction conditions and the reaction time, you can grow these anisotropic nanostructures.
Hola Guille, buen día, ¿cómo estás?
Yeah. So these nanostructures are 200 nanometer long and 30 nanometer wide, more or less. So how do we create, how do we orient such small nanostructures on a substrate with long range order? What we do is we start from a solution that has a dispersion of the nanobelts in water and ethanol, and we have a basin that is like 6 centimeters by 3. I mean, you can check the experimental details in the paper. But this basin is filled with water, and we use a syringe pump to inject a dispersion of the nanobelts on the water surface. So controlling the injected volume and the time, we can stack these nanobelts to form a full film on the water surface. And then with a substrate, we collect this film and create the oriented copper hydroxide substrate, which can then be converted to an oriented MOF film. typically this step was performed manually, but we found that when you want to make a large amount of samples, this has some problems because it creates results that are quite, the reproducibility is low. So before I show these results, I want to quickly explain how we measure the degree of orientation of these films, because it's parameter basically that we use to compare different samples. So basically what we do is based on the X-ray diffraction measurements from the normal out-of-plane Bragg-Brentano XRD, we select the 002 reflection of the copper hydroxide that is around 34 degrees. And keeping the source and detector on that configuration, if you rotate the sample and collect the intensity, you get an azimuthal profile of the X-ray diffraction. And if the sample was not oriented, you would get basically a flat line because the intensity would be the same for all the azimuthal angles, for all the angles of the sample in plane. But if you have a profile that looks like this with peaks that are separated by 180 degrees because of the symmetry, this means that there is a preferential orientation in the sample. And the sharper these peaks are, it means that the more oriented the sample is. So what we want to do is to get basically the sharpest distribution that we can. We used the full width half maximum to quantify this, and we use a sort of normalization of this parameter that we call alpha, which it has a value of 1 when we have full uniaxial orientation. What's interesting, I'm not discussing it in detail here, but you can find more info in the paper, is that our friends Thomas and Egbert calculated that this the real distribution, the angular distribution of the nanobelts of the physical system is directly related to this width of our azimuthal profile measurement. So really, this value is a measure of of the dispersion that we have in the positions of the nanobelts and the angular distribution. So we call this alpha the orientation, and we want to have it as high as possible. And then we also want to evaluate the homogeneity of the film, because due to the deposition method, many times we notice that we have cracks or bubbles or dishomogeneities on the film. So basically, just by evaluating from optical images from the samples, we want to evaluate how much percentage of the substrate is coated with an homogeneous layer. So this is what we call coverage, and we want to have as high as possible. So with this in mind, we perform many samples with the typical manual procedure, and we observe that we have around 50% of the samples that have orientation that is below 0.7. That could be our threshold for the quality that we want to have, and with a wide range of dishomogeneous coverage, let's say. So ideally, we would like to be on this top corner with the highest orientation, the highest coverage. And importantly, this is also very operator independent. So the problem with this is that really the quality of the substrate is directly impacting on the quality of the MOF film. Initially, I mean, we knew this would be extremely important, but we didn't know to what extent the MOF copies exactly the orientation of substrate, and we found that it's really does, because here I have samples with 3 different orientation degrees, and this is an SEM image of the copper hydroxide substrates, and this is with the MOF after exposure to terephthalic acid. And what we find also in the azimuthal profiles is that the width of the azimuthal profile following the MOF peak is copying almost exactly the width of the distribution from the copper hydroxide. So really, if we want to improve our MOF coatings, our MOF films, we need to get the best copper hydroxide substrate that we can have. So what we did was to improve the deposition procedure and introduce a deep coater to control the final step and to be able to control the immersion depth and immersion speed. And also we explored different injection volumes with the syringe pump and tried to obtain the best coatings that we could get. The first parameter that we identified was very relevant was the leveling of the substrate. So it's not that we tilted the substrate on purpose, but we found that typical deep coaters devices do not have such a good precision on leveling the sample. And actually, initially, with a tilting of the sample that was almost imperceptible to us, we found that this was impacting a lot on the quality of the samples. For angles above 0.6, we have cracks and bubbles. And then even for very small tilting that is between 0 and 0.6, which was hard to see, we would get homogeneous coatings. But if you look at the orientation, actually, the orientation was worse than when we finally used a perfectly leveled 0-degree tilting sample holder, which requires a precision of tilting up below 200 microns. So initially, we didn't know that this kind of precision was needed. So this was the first challenge that we could overcome for this. Then we studied with a perfectly leveled sample holder. We studied the immersion depth. So we were comparing always the coverage and the orientation because in principle we want to improve both or find a parameter that has a compromise between the best coverage and the best orientation. And we found in this case that for an immersion depth of 1.5 millimeters, we had the best orientation and very good coverage. Then we studied the immersion speed and we found a clear trend in the coverage that is improving with a higher speed. And the higher speed also had the best reproducibility of this set, if we look at the error bars. And then we studied with a fixed immersion depth and fixed immersion speed. We studied different volumes that we could inject on the water basin, and we found also a clear trend where the coverage and the orientation are both improving until this point. So we chose 69 microliters of the solution as the chosen volume. So this optimization process allowed us to improve both the coverage and the orientation of the degree of orientation of the substrates. It allowed us to move from this cloud of gray points, let's say that was the quality of the samples that we were obtaining with the manual procedure, towards this corner here, that is what we really want, the best coverage and the best orientation that we could have. We actually obtained 100% of the samples with the orientation above 0.7 and all of them also with the coverage above 95%. Importantly, this also allowed us to increase the substrate size that we could coat. I think this is, for me, one of the most important conclusions of this is that we were able to improve substantially the reproducibility and the coated area. So initially we were working with 1 centimeter by 1 centimeter samples, substrates, and we were able to finally improve this until 3.2 by 3.2. So these are the largest wafers that we could cover with a good homogeneity and orientation degree. And also this method allows for the deposition of multi-layered films that still maintain the orientation. So in this example, 5 layers of nanobelts are deposited one after the other, and they have it requires a control that you cannot have with the manual procedure. So basically, some conclusions, we were able to improve the reproducibility substantially from a 15% variation that we had in the orientation with the manual and down to 1% variation with the automatic protocol. We had 100% samples with a high orientation about 0.7 and also all of the samples with coverage about 95%. And we were able to increase the substrate size that could be coated. This is interesting because the quality, as I talked before, the quality of the copper hydroxide substrates impacts directly on the quality of the MOF film. So this could allow to increase the throughput of the fabrication of oriented MOF thin films and could be used for multi-layer structures and be interesting for MOF-based device fabrication. I want to finish thanking again the group and our collaborators here in Graz in Austria and collaborators from different parts from Australia, from Japan, and also the funding. Without this funding, it wouldn't have been possible. Most of this work was funded by an ERC and also by the TU Graz Lead project, that is an internal project of the university. And thank you very much for your attention, and I am open for questions on this work.
Gracias, Mercedes. Muy interesante tu charla. Thanks a lot, Mercedes, for a really interesting talk. Hot topic, the films, oriented films, always interested us. So I have a little question. So maybe you did try it right. Maybe it's not doable. So please correct me if I'm wrong. You mentioned that when you surface position your nanobelts on the liquid surface in order to, let's say, fish these nanobelts to grow later on these MOF films, there was of course, some problem with reproducibility regarding the orientation of the nanobelts, the volumes you use, let's say concentrations, I'm guessing, of the colloidal suspension of the nanobelts. I don't know. I was wondering, what is the monodispersity of these nanobelts, if you know that, and then whether you think or not that it's possible to use a Langmuir bloodshed apparatus to, let's say, control the surface concentration of those nanobelts and even maybe the orientation.
Thank you, Matthias. These are really good questions, actually. For the monodispersity, I have some measurements that were taken from AFM topography. So the dispersion in width is quite low, but in length, we have from 100 to 400 nanometer length. I mean, this definitely will have an influence on the highest degree of orientation that we can have. If you saw that we never have one, I mean, the highest that we have obtained is, maybe this might be improved a little bit. I think the highest was 0.85 or something, but there is also just I have seen works where they model pneumatic systems, and there is a fundamental limitation when considering the aspect ratio of the nanobelts. So if you have, like, for this aspect ratio, there is not a lot of improvement that can be obtained just because of the dispersity of the nanobelts in sizes. And we have, for the other question, we have tried Langmuir bloodshed approach. In this case, we found that these were extremely small for our setup. So we were not successful in the test that we did. We welcome anyone who wants to try this if they have a better solution.
Yeah, no, it's challenging. It's challenging.
Yeah.
Maybe I was thinking maybe using some, let's say, some stabilizing agent as a polymer for a surface functionalization of your nanobelts maybe increasing or decreasing, just play with the interactions between coating or not coated, or I don't know how difficult it is, but I imagine something like that.
Yeah, these are very interesting ideas. We haven't tried this, so it could be a following step.
Yeah, good. Okay, happy to
Thank you.
jump in if you consider it. Yeah. So there is another question from the audience, thanking you for your talk, and it says like, does the surface of copper change the oriented surface growth? I mean, whether you use different salts like nitrate, chloride, or another salt for your copper hydroxide synthesis?
Well, we have not tried to synthesize the copper hydroxide nanobelts from other metal sources, from other metal salts. So I would not know. I mean, we always synthesize the MOFs, at least the first layer, from the ceramic to MOF conversion from copper hydroxide. In this case, no, we have. I mean, you can create these MOFs. You can synthesize them solvothermally using other salts. So I wouldn't know. I mean, from this mechanism of conversion, I wouldn't know how to compare it.
Yeah, I assume that in this case that when you try to synthesize MOFs from different metal salts, like using, let's say, nitrate, chloride, or whatever, usually the yields change, and sometimes even the structure you get is substantially changed. So maybe the question referred to that, but I'm thinking you are not playing with that parameter, but using your product for creating your oriented film.
Yes, right? I mean, in this case, what's interesting about this ceramic to MOF conversion is that it's very fast. For example, I mean, the conversion times are a couple of minutes. So this is different, I would say, to the kind of kinetics that you have with solvothermal synthesis. And we need this heteroepitaxial growth mechanism to retain the orientation. Otherwise, you wouldn't have macroscopically oriented MOF. So it is intrinsically different to a mechanism where you use the other metal salts.
Mm-hmm. And the last one from Juan Samaro, also from the organizing committee in Santa Fe. Maybe when you get back here, we can get together.
That would be lovely.
In person. Dice, which application do you think is potentially more interesting for these really nicely aligned surfaces that you create?
Well, in principle, any kind of application that requires the oriented pore channel, so anything that benefits from diffusion processes or host-guest interactions that require the high diffusion or improved in that sense. So it could be sensing or, yeah, I mean, a specific application. We would have to think about this also depending on the MOF.
De acuerdo. La pregunta la hice yo, Mercedes. Sí, perdón. Muy buena la charla, me gustó mucho. Y no, simplemente era porque me generaba esa curiosidad de cuál vos pensabas. Primero, bueno, si lo habían utilizado en alguna aplicación en concreto, o si no quedaba en digamos, en una situación potencial como para diferentes, como estás comentándolo vos, para diferentes usos.
Por ejemplo, en el Nature Materials se trabajó, o sea, se aplicó usando una molécula que tenía propiedades de fluorescencia y como una especie de sensor de polarización. Ahora no me acuerdo exactamente para qué lo usaron, pero lo interesante era como los poros están orientados, puede también orientar a una guest molecule que te pueda interesar y después eso puede tener aplicaciones ópticas interesantes.
Claro. Ah, perfecto. Ese es el campo en donde estas estructuras ordenadas podrían tener una
Es
aplicación
uno de los
fuerte.
ejemplos que fue
Claro.
el que más se exploró en las publicaciones hasta ahora.
Bueno, gracias Mercedes por tu charla.
De nada, gracias por la pregunta.
Gracias, Juan, por participar. Y bueno, María, con esto te vamos a despedir, agradeciéndote mucho por haberte sumado y bueno, esperando que tengas todo el éxito posible ahí en GRAS y bueno, tenerte pronto en Argentina de nuevo.
Muchas gracias. Estoy ansiosa por volver y interactuar ahora siempre que la pandemia lo permita.
Sí, ya lo vamos a hacer, vamos a interactuar. No te preocupes,
Muchas gracias.
algún asado va a haber. Bueno,
Sí, gracias por la invitación. Chao.
well, thank you, Maria, for his presentation. We move to the next second speaker on these flash presentations. Also from Argentina, Rodo Acosta, de la Universidad Nacional de Córdoba, nos engalana la sesión flash.